Alright, so in this video we're going to do another center of mass problem, but this one a little bit more complicated than just a two-case scenario. So let's talk about how we are going to figure this out. So it's not just going to be a straight example, we're going to work through some thinking process here. So let's set up our problem. So let's say we have a nice canoe here with, let's do a Romeo and Juliet. So we'll do Romeo down here, and we'll put Juliet down on this end. Obviously this is the canoe. So this is our setup. So okay, cool. Let's establish a coordinate system. And so one of the things that we've learned is that it's probably best to establish a coordinate system in which is going to be closest to the center of mass, or the object we're looking for. So let's do a similar scenario. So let's say, okay, we have the mass of Romeo, so we know the mass of Juliet, and the mass of the canoe. So I'm just going to say Romeo is 80 kilograms, and Juliet maybe is 70, and the canoe is, I don't know, 60. I'm just making up stuff. Okay, so we know that, and let's give our canoe a length. Let's say the length of the canoe, say length L. Length of the canoe is, I don't know, 2.5 meters or something. Okay, so this is what we know. And so we're going to have Romeo start on one end, and he's going to walk to the other end to see Juliet. So when he does this, all of our forces are internal forces, and so when he moves this way, the canoe is obviously going to move the other direction, but so is Juliet. And so the question's the same as before. Okay, well, if Romeo moves from here to there, how far does the canoe move in this scenario? So we're looking for the x position of the canoe. So okay, cool. So let's go ahead and establish a coordinate system. So the center mass of the canoe should be in the center of the canoe. Juliet should be in the center of Juliet, and Romeo's should be here. So if we're looking at this in one dimension, we would say that here's a dimension, and let's go ahead and put the origin here at the center. So this is the canoe center mass, Juliet center mass, and Romeo center mass. So this is our initial setup, and then what's going to happen is, well, we need to find our center mass because that won't move. So we go, okay, let's go ahead and find the center mass, our initial center mass. So we go, okay. So it's the sum of xi, mi, from I to n or whatever, over your total mass. Okay. So let's go about this. So let's start with Romeo. Romeo is at one end of the canoe, so he is, since we'll establish this is negative and positive, that's important. So he's a negative distance from the center of the canoe. So that'd be 1.25 meters times his mass, which is 80 kilograms. Oh, 80. All right, then we do plus the mass of the canoe, well, its distance times its mass, so that'd be 60 kilograms. Then plus Juliet, who is at the opposite end, so she's at 125 meters times her mass of 70 kilograms. Okay, and then we do all of that, we divide it by the total mass, which would be 80 plus 70 plus 60 kilograms. So here for x center mass, obviously this is 0, so we do negative, type this in the calculator, negative 1.25 times 80 gives us negative 100 meter kilograms. So this times 70, get 87.5, and then 80 plus 70 plus 60 gives us a total mass of 210. Okay. So now we're going to take these. So I'm going to add 87.5 plus a negative 100. And we get negative 12.5 meter kilograms over 210 kilograms. So we divide by 210. And we get a center of mass at negative 0.0, let's say 596 meters. So that's, this distance is 1.25, and this is positive 1.25. Wow, that looks terrible. It's all negative and positive. So this thing is going to be like 5 centimeters right here, which makes sense because the canoe's not going to contribute anything, and the Juliet's almost the same mass as Romeo, so Romeo's a little bit heavier, so it's going to be a little bit to the left side here. Okay, sure. So once he moves, we can establish a new setup here. So the center of mass is going to remain here, so I'm going to try to draw that in about the same spot. This is still 1.25, negative 1.25, except now, this is still our origin, right here, origin. This is our center mass. Just gonna label that. So now, Romeo's going to move this way, and the center mass is going to stay in the same place. So what's going to happen is, in terms of the picture, now Romeo's going to be down here. So if I redraw this canoe, let's see. Draw best I can, okay? So now we're going to have something like this, where we have the center mass of the canoe here, and then Romeo and Juliet are down on this end, right? Both of their center masses, we're going to say, are basically in the same spot for simplicity's sake. So we're trying to figure out how far the canoe moved. Well, it's obviously this distance, from here to there, right? That's what we're trying to figure out. How far is that? Okay, well, let's think here. It's a little bit more complicated, because before, when he moved, we said, oh, it's this far. So when Romeo was the only one on the boat, it was just the mirrored scenario. Fairly straightforward. This one is a little bit more complex. So you go, okay, well, how am I going to solve this? Well, probably the easiest thing is to figure out where everything is. So we can use the center of mass equation. We're essentially going to work it backwards, because in our setup here, the origin hasn't moved and the center of mass hasn't moved. So the center of mass of our system, since all of the forces are internal forces, the center of mass will continue to do what it was doing. In this case, it wasn't moving, so it's not moving here. So it's in the same spot as before. So literally, I can just set up an equation. And I say, okay, XCM, this is the new one, if you will, but it's the same as the old. But now we're calculating the new spot. So we set it up. We got to do one for each person. And we go, okay, well, let's write down the masses first. We know those for sure. So we got Romeo's mass is 80 kilograms, plus the canoe's mass is 60 kilograms, plus Juliet's mass is 70 kilograms. Okay. And the total mass stays the same, so it's still all over 210. That's easy. And we know that XCM, well, the XCM is the exact same as it was before. We actually know that this is this negative 0.0596, or whatever I called it. Okay, so we know that. So we can essentially solve for something on this side, and that's going to be good because we don't actually know what what distances these things are. Now we know that Romeo has moved from one end to the other, but the problem is now we're trying to figure out how far from the origin these things are, and we don't know. So we have to sit down and give a little thought to this. So if we look at our picture here, try to move this so you can see it best you can. So if we're trying to do this, we go, okay, maybe it's simpler to draw a bigger picture. This is the distance that we're looking for. Okay. Now, we know where the center of mass is. We know that, first of all, wherever Romeo is, that's where Juliet is. Okay. So whatever distance, let's say Romeo's distance, his position is the same as Juliet's position. So I'm just going to call it X Romeo, X Juliet. It's the same. I'm not going to label them differently. So that's what I'm saying. They're basically in the same spot. Okay, well, how is that related to the center of mass of the canoe? Now, that's actually something that we know. We know that she is at one end and she stayed there. So she is 1.25 meters, or half the length of the canoe, from the center of mass of the canoe. So the distance from here to here is this 1.25. Cool. Now, we're trying to figure out how far the center of mass of the canoe has gone this distance. Well, this 1.25 is going to be this distance. So we got center mass here, and we have this here. So we have to figure out an equation to write how far the center of mass has gone. So what we can do is, this is 1.25, or the length of the canoe divided by 2. And if we're looking at the canoe, there's a little bit of a brain fart. Okay, so we've already established this. So this distance is from the center of the canoe, not the canoe. This distance is Romeo's distance from the origin. So we can set up a little equation here, because the problem is we have one equation, and these two are the same unknown, but this is going to be a different unknown. So we can't have one equation with two unknowns. We need a third, or a second equation. So we're going to build a second equation here. So generically, we could say that L over 2, the length of the canoe over 2, should equal the distance the canoe is from the origin plus the distance Romeo is from the origin. Right? So this is the distance the canoe is from the origin. This is the distance Romeo is from the origin. Let's call this X sub C here. And those should add up to half the length of the canoe. Well, in this case, we know the length of the canoe is 1.25 meters. So we could say 1.25 equals XC plus XR. And that gives us another equation here. So here I can write this as the center of mass of the canoe. And again, one equation, two unknowns isn't going to work, so we'll solve this one for one of them. In this case, since we're trying to figure out how far the canoe went, I'm going to solve this for Romeo's distance, so I can eliminate Romeo's distance over here, so I can just solve for the variable that I'm interested in this case, how far the canoe went. So, if we do this here, we can subtract XR from both sides. Oh no, right, subtract XC. Because I want to solve for, I want to replace XR. Right? So XR equals 1.25 minus XC. So I can replace that over here, and I can say negative 0.0596 meters equals, instead of XR, I'm going to say 1.25 minus XC times 80 plus XC times 60 plus 1.25 minus xc times 70 all over 210. So let's hope that I don't mess up any of the math at this point. 0.0596. So now it's just an algebra problem, if I've done everything correctly. So I get 1.25 times, times 80, so I get 100 minus 80 xc. I'm going to leave out the units so it doesn't look too bad here. So that gives me 60 xc minus another 70 xc, and then do 70 times 1.25. Redistribute, so this is plus another 87.5. So here we can add these up, still all over 210. Minus 0.0596. So we get 187.5. That's pretty straightforward. So 80, 70, so we get 90 here. So 90 xc. So I'm just going to go ahead and multiply 210 on both sides. So I get this thing off the bottom. So do times 210 times negative 0.0596. So we get 12, negative 12.516. 5 minus 90 xc minus 187.5. I messed up a sign here. I'm looking at it. Negative 200. 6 equals negative 90 xc. Negative 90 xc. Yeah, 2.2. Repeating essentially meters. So that means this thing has moved 2.2 meters this way. So that means the center mass is, well, obviously going to be very close to them. So my drawing isn't very good, but that would be our solution. So here the generic solution is to just find your center of mass first, then use that center of mass in the second, do it again, but use that same number in here, and then just solve for whatever system you're looking for. So the key there was finding another equation, which we needed right here. So this distance that it moved, from the center to Romeo is half the length of the canoe, and then those two should add up, from the center of the canoe to the origin, and then from the origin to Romeo will give us this whole distance. So we need this equation along with our center of mass equation to find the center of mass. So hopefully that helps you solve a center of mass problem for any amount of variables. Obviously, if you put more and more items in here, it gets a little bit more complicated because of what you're going to have to do up here, but overall it's the same process.